everybody. Today we're going to talk about the first derivative test. To get ready for that though, let's review a little bit. Here I have a graph that kind of goes up and down and back up again, and I want to find the increasing and decreasing intervals of the function. So what we want to notice is that I should read from left to right, just like I read words, I would read math. So starting over the left, I'm starting at negative infinity. And I can see the graph is going up, so I want to see where does it stop. And it looks like it stops right about here, which would be the x value of -5. So from negative infinity until -5, I would want to say that I am increasing. So I'm only giving x values here, I don't talk about the y. Then from the -5, it starts to go down, so I would say then from -5, and I look at where does it stop, and that would be at -2. And I could see it was decreasing. So increasing INC, decreasing DEC. Then at -2, it goes up again. So I'm going to go back up to that first interval and put a U for union in between and say from -2 and then to infinity, because it continues to increase after -2. So I have negative infinity to -5 and then -2 to infinity. Those were my increasing intervals. Notice those intervals are all open. So I have these open parentheses on all of my intervals. So that was my first part, was my increasing. And then I have from -5 to -2, that's where it was decreasing. I want to pay particular attention to these places where it changed at the -5 and -2. So up here at -5, we can see that this point is higher than the numbers on the left and the numbers on the right. We would call this a local maximum, and I'm just going to write local max to say it's higher. And then at -2, it's a local minimum. It's lower than the points on the left and the right, so let's write that as a local min. So I want you to see that these places where it changed were maximum and minima. Sometimes we call that extrema, just saying extreme values, so max or min. So good to see, good to be reminded of. Let's look at that on another graph. Here's my second graph, and same thing. I want to look at where is it increasing, where is it decreasing. So I'm starting once again on the left, so that's negative infinity, and I can see it's going up. But this time, it doesn't reach a maximum. It just kind of goes up until I got to 0. And then from 0 to infinity, so let's write that, 0 to infinity, it was going down. Now, this is also open, so negative infinity to 0 and 0 to infinity, two separate intervals, both of them open, but they're open for different reasons this time. This is open because it never reaches 0. If I kind of zoomed in on the graph more, you would see I would get closer and closer to the y-axis as I go close to 0, but I don't actually touch 0. So we have two different ways that the function can change. It can change when it gets to an extrema. It can also change when it finds a place of discontinuity. So we want to keep that in mind of where do things change. It can change at extrema. It can change when the function just has a break. So that's what we're seeing here. So let's kind of give a note about that. So my note is a function can change from increasing to decreasing when it reaches a maxima or minima of the function, or when there is a point of discontinuity in the function. And when I say increase to decrease, also decrease to increase. But a function can change, so at an extrema or at discontinuity. The x values where a function changes are called partition numbers, so keep that in mind. Two different things happen to get a partition number. The points where the function has a local max or a local min are called the critical numbers. I want you to be careful with this wording. If I say critical number, it's only an x value. If I say critical point, then I want you to give me both an x and a y. So watch that. Number singular, point 2. Critical numbers occur at values in the domain where the function has a derivative of 0, so f prime of x equals 0. Partition numbers occur when the derivative is 0 and where f prime of x does not exist. So partition numbers, two things can happen. I can have the derivative is 0. I can also have the derivative doesn't exist. So watch for that. We're going to check for two things when we look for partition numbers. All partition numbers will not be critical points. Some of them will, some of them won't. Again, we'll talk it through. So here's our first example. Let's find the partition numbers of f of x equals x squared minus 2x plus 5. So what you're going to get used to is you're going to take the derivative. That's not a surprise. Here's 2x minus 2. So x squared minus 2x plus 5. Derivative is 2x minus 2. And our new thing is just set that equal to 0. 2x minus 2 is 0. Says 2x is 2. X is 1. So we have one partition number this time. There's not a place where 2x minus 2 is undefined. Let's take a second look. Let's find the partition numbers of f of x is 4 over x plus 9. So I need to take the derivative, and you have a couple choices. You could do the quotient rule because you have a quotient, but instead I'm going to do this as the chain rule. So my first step will be rewrite this as 4 times x plus 9 to the negative 1. Then when I take the derivative, that negative 1 comes down. I have negative 4 x plus 9 to the negative 2. And then you're thinking about x plus 9, the derivative is 1. I'll write it for emphasis. So my derivative that we got was negative 4 over x plus 9 squared. I want to take that and set it equal to 0. So I have negative 4 over x plus 9 squared. I want you to get used to the idea that the only way a fraction is equal to 0 is if a is equal to 0, right? So when I have a fraction, I'm really just looking at the numerator. Negative 4 is never equal to 0. So this one, f prime of x, is not going to be equal to 0. So I don't have anything from that. For partition numbers, we said two things happen. We need to look at where is the derivative equal to 0 and where is the derivative undefined. So undefined would be when is x plus 9 squared equal to 0, which is x plus 9 equals 0. So we have x equals negative 9. So I do have a partition number at the negative 9 because something's going to happen. That's a place of discontinuity. Once we have the partition numbers, we're ready to talk about the first derivative test. So the first derivative test gives us a step for finding out increasing, decreasing intervals of a function. The first step is to break the domain of f of x into intervals based on the partition numbers of the function. Then in each of the intervals, you're going to pick a test point. Now, I don't really mean point like x, y, I just mean a test value. So you're going to pick some number in that interval and use it to test. And what you're going to test is the sign of the derivative. So you're going to take that number, you're going to plug it into the derivative, but you only care about the sign. So you don't really care what number it is, you just care, is that number positive or negative? If the number is positive, so that means if f prime of x is greater than 0, then you know the function is increasing over that interval. If, when you plug that number in, you get a negative, then you know the function is decreasing. So positives will go up, and negatives will go down. So we're going to do a bunch of examples to make sure we're comfortable with this new first derivative test. We're going to find the increasing, decreasing intervals, and then after that we'll be able to find the local extrema. So let's start with f of x is 1/3 of x cubed minus 2x squared minus 5x plus 8. Now step 1 said we need to break up the domain using the partition numbers. So what are we going to do? We're going to take the derivative. So f prime of x will be equal to 1/3 of x cubed is x squared, negative 2x squared is minus 4x, negative 5x is minus 5, the derivative of 8 is 0. So I have my derivative. I set it equal to 0. I have x minus 5 times x plus 1 when I factor. So I have x is 5 and I have x is negative 1. So these are my partition numbers. The domain of this function, because it's a polynomial, is all real numbers. So I'm going to draw the real number line. I'm going to put these two numbers on. Here's negative 1, here's 5. I don't need any other numbers. And now I'm going to break this up. So I'm going to say this is negative infinity to negative 1, negative 1 to 5, and then 5 to infinity. So I took the real number line and I used the partition to make intervals. I'm going to make a chart out of this. So we broke up our domain. Now we're going to pick a test point. So I just need to pick anything from negative infinity to negative 1. Let's say we pick negative 2. Anything from negative 1 to 5, let's say 0. And then 5 to infinity, I'm going to pick 6. It doesn't matter what number you pick as long as that number is in the interval. Do not pick the partition numbers themselves. So don't pick negative 1, don't pick 5. That doesn't work. Okay. What are you going to do with that? You're going to put it into the derivative. I tend to put it into the little pieces, so I'm going to put it into x minus 5 times x plus 1, but if you want to put it into the whole thing, you could do that too. All right, so I think negative 2 minus 5 is negative. Negative 2 plus 1 is negative. A negative times a negative is a positive. So this is me testing the sign of the derivative. 0 minus 5 is negative. 0 plus 1 is positive. So again, 0 went into these factors and I said, what sign do I get? A negative times a positive is a negative. 6 minus 5 is positive. 6 plus 1 is positive. A positive times a positive is a positive. So we broke up our interval, we picked a test point, We tested the sign of the derivative using the test point. Now we're ready to decide, what does this mean? Positive for the derivative says this is increasing from negative infinity to negative 1. Then it will decrease from negative 1 to 5. And last, it will increase from 5 to infinity. So we did the first part. We found the increasing, decreasing intervals of our function, but now we want to find the local extrema. Well, let's think this out. Increasing went up until it got to negative 1, and then it went down. So you can see what happens if I go up and then I go down. That means I get a maximum. So I have a max, and we can call it a local max, when x is equal to negative 1. And then it went down and then up, so down then up. We can look at that. That looks like a minimum. I have a local min when x is equal to 5. If the question asks you what the max is, what the min is, or if it asks for a point, then you need to plug this back in, plug in the negative 1, plug in the 5, but plug it into the original function. Don't plug it into the derivative. So let's quickly look at that. So if I had to do that, I would use Desmos or a graphing calculator, and I would plug in f of x is equal to 1/3 of x cubed minus 2x squared minus 5x plus 8. Then we can find f of negative 1 and f of 5. Okay, so at negative 1 it says 10.67, and at 5 it says negative 25.33. You can also see on our graph that we have at negative 1 there's 10.67 as our maximum, and there's our minimum at 5, negative 25.33. So let's write that in. I have negative 1, it was 10.67, and then at 5 we had negative 25.33. Let's try another function. This time I have g of x is x squared over x plus 7. Same thing, want to find the increasing, decreasing, and then the extrema. This one I do need to use the quotient rule, so let's start. F prime of x is equal to low x plus 7, d high, which would be 2x, minus high, which is x squared, d low, the derivative of x plus 7 is 1, and that's all over x plus 7 squared. We can distribute this out. So 2x times x is 2x squared. 2x times 7 is 14x. And then I have minus x squared over x plus 7 squared. The 2x squared minus x squared gives us x squared plus 14x over x plus 7 squared. I'm going to take this and set it equal to 0. That means I want to take the numerator. X squared plus 14x, set it equal to 0. And x comes out, I have x plus 14. So I get two numbers here. I get x is 0, I get x is negative 14. So there's two partition numbers. We have a third partition number from taking the x plus 7 in the denominator, setting it equal to 0, and I get x is negative 7. So the negative 7, the 0, and the negative 14 are partition numbers. So I'm again going to write those on a real number line. So negative 14 comes first, then negative 7, and then 0. You'll start to see you'll always have one more interval than the number of partitions. So this is negative infinity to negative 14, negative 14 to negative 7, negative 7 to 0, and then 0 to infinity. You pick a number. Let's say I pick negative 15, negative 14 to negative 7, I'm going to pick negative 8, negative 7 to 0, I like negative 1, and then 0 to infinity, I'm picking 1. I'm going to put that into the derivative, and the x plus 7 squared in the bottom will always be positive. So if you wanted to, you could go ahead and write in a fraction and say, I know the denominator is positive because it's squared. Then negative 15 as x is negative. Negative 15 plus 14 is also negative. Negative, negative, positive is positive. It's increasing in our first interval. Negative 8 is negative. But negative 8 plus 14 is positive. Negative, positive, positive is negative. This says decrease. When I plug in negative 1, that's negative. Negative 1 plus 14 is positive. Negative, positive, positive, again negative, which is decreasing. Last one, 1 is positive. 1 plus 14 is positive. All positives positive, that's increasing. So we can see from negative infinity to negative 14, it was increasing. Negative 14 to negative 7, decreasing. Negative 7 to 0, also decreasing. 0 to infinity, increasing. My second part says find the local extrema. When I'm looking at the extrema, the only extrema could be the negative 14 or the 0. 7 is a partition number. That means it can't be a max or a min. Partition meaning it was a place of discontinuity. 14 and 0 were also partition, but we know we don't have to look at the negative 7, only the 14 and 0. Those are our critical numbers. So what do I want to look at? I want to look at it went up, increasing, and then it went down, decreasing. So I do have a max. So I have a local max at negative 14. And then this decrease, increase, there's a min. So I have a local min at 0. Now we can look back to the beginning and see what the y values would be. Our original function was x squared over x plus 7. If I put in 0, 0 squared over 0 plus 7, that's going to give me 0. So I have a local min at 0, 0. And then the other one said negative 14. So I'm going to quickly throw that in my calculator. It gave me negative 28. So my max, negative 14, negative 28, my min is 0, 0. Now this is interesting and important for you to see. Do you see the y value negative 28 and this y value of 0? Negative 28 is smaller than 0, but that doesn't mean it has to be the min, not the max. See how it's kind of backwards thinking there? Let's look at the graph really quick so I can show you what that looks like. So here I typed in x squared over x plus 7, and then I'm going to move my graph over so you can see it. So you can see down here, this 0, 0, there's a min. It went down and then up, so the min at 0, 0. And then this up and down, which we can see at negative 14, negative 28, was our max. So you can't go by the numeric value. You have to go by the increasing, decreasing of the functions to decide if it's a max or a min. So back to polynomials, and this one says f of x is x cubed minus 12x squared plus 36x minus 15. We're going to start with increasing, decreasing. F prime of x is 3x squared minus 24x plus 36. Luckily, 3, 24, and 36 are divisible by 3. Let's take that 3 out. I get x squared minus 8x plus 12. Now I'm trying to set this equal to 0. So we want to factor. So I want to find factors of 12 that give me 8. Well, that would be 6 and 2. And they're both subtracted because it's a negative 8. So I have x is 2 and I have x is 6. All right, so this was my first derivative equal to 0. This one has a domain of negative infinity to infinity because it's a polynomial, so I don't have to worry about any places where the derivative is undefined. I have 3 intervals, negative infinity to 2, 2 to 6, and then 6 to infinity. Maybe you're trying to pick up on how I pick numbers. Negative infinity to 2, let's say I pick 1. 2 to 6, let's pick 3. 6 to infinity, let's pick 7. When I put the derivative in so that I can test the sign, don't forget about the 3, because the sign could make a difference, right? So maybe it wasn't a 3, maybe it was a negative 3. It would make a difference in the derivative. So don't throw anything away. Make sure you're always going back to the derivative as a whole, not to pieces that were factored. So I have 3, which was positive. 1 minus 2 is negative. 1 minus 6 is negative. Negative, negative, positive, increasing. Then I put in 3. So my beginning 3 is positive. 3 minus 2 is positive, but 3 minus 6 is negative. So positive, positive, negative, negative, decrease. Last one is 7. The 3 was positive. 7 minus 2, positive. 7 minus 6, positive. That's all positive, and it's increasing. Just again, pointing out, what are we doing? We're only testing the sign. We don't care about what number the derivative is. But if you wanted to, you could always plug the derivative in. I could put 3x squared minus 24x plus 36 into Desmos or something. Plug in 1, plug in 3, plug in 7. Get the positive, negative. That would work also. So now I know my increasing, decreasing intervals. I have that other question of what are my extrema? So up, down, there's a max. Down, up, there's a min. So I can see my max and my min. So the max happened at 2, and my min happened at 6. And again, just for good form, I want to make sure we understand that to get the y values, I plug it into the original, which was x cubed minus 12x squared plus 36x minus 15. Okay, so I've typed in my function. Now I'm going to type in f of 2, f of 6. F of 2 gave me 17. F of 6 gave me negative 15. We could also look over at the graph and click on it, and it'll tell us there's our max at 217 and our min as 6, negative 15. So let me write that back in, 217 and 6, negative 15. This one says find the increasing decreasing intervals of f of x is 2x plus 32 over x. Then one more time find the local extrema. So let's start with the derivative, but I kind of want to rewrite the function first. So I'm going to say 2x plus 32x to the negative 1. I want to use the power rule, so I need to express everything as powers. Derivative. 2x becomes 2. The 32x to the negative 1, that negative 1 comes down. I have 32x to the negative 2. What am I going to do? I'm going to set that equal to 0. So I'm going to write it as 2 minus 32 over x squared equals 0. That way it's written back as a fraction. I'm going to move the 32 over x squared to the right. I have 2 equals 32 over x squared. And then I can kind of like cross multiply, right? So 2 times x squared equals 32. That says x squared is equal to 16. I have x is plus or minus 4. So this is what I get from taking the derivative and setting it equal to 0. Also remember, we have to look at where is the derivative undefined. Well, the derivative would be undefined here, where this 32 over x squared is. So I know I can't put a 0 down there, so I also have x equals 0 that we need to look at. So when I set up my intervals, I'm going to go negative 4, 0, and 4. Don't miss that 0. That would change things. So I want to go negative infinity to negative 4, negative 4 to 0, 0 to 4, and then 4 to infinity. So 3 partition numbers, I have 4 intervals. I'm going to pick a point. Let's say I pick negative 5, let's pick negative 1, positive 1, and 5. So something at each interval. And what am I testing? I'm testing the sign of the derivative. So probably the easiest way to see the derivative was 2 minus 32 over x squared. So this time when I plug it in, I really need to pay attention to what I get. So 2 minus 32 over x squared is 2 minus 32 over negative 5 squared. If you want to use your calculator, that's fine. I have 2 minus 32 over 25. 2 minus 32 over 25. 32 over 25 is just a little bit bigger than 1, so 2 minus that is going to be positive, so we're increasing right here. Same thing, 2 minus 32 over negative 1 squared. Well, this is 2 minus 32. That's negative, so it's decreasing. Same exact thing is going to happen when I plug in 1. I get 2 minus 32 over 1, which is 2 minus 32. That's negative, still decreasing. And then at 5, I have 2 minus 32 over 5 squared. Looks like the first part. 2 minus 32 over 25. That's positive, so it's increasing. 0 cannot be an extrema because it's a place where the derivative was undefined. So my only extrema could be at the positive or negative 4. So I look at this up, down, I can see a max. I look at down, up, I can see a min. We would want to plug those back into the original to get the actual extrema. So let's write that as negative 4 and then positive 4. I'm plugging them back into the original. So I'll write it up here. F of 4 would be 2 times 4 plus 32 over 4. This is just skipping using the calculator. So 2 times 4 is 8. 32 over 4 is also 8. 8 and 8 is 16. So we know at 4 we get 16. So 416 is our local min. And then let's do the same thing with negative 4, and I'll do it the same way. I'll have f of negative 4 is 2 times negative 4 plus 32 over negative 4. 2 times negative 4 is negative 8. 32 over negative 4 is negative 8. 8 and negative 8 is negative 16, so that's kind of similar. So let's go back down and say negative 4, negative 16 was our local max. Now, when you're doing homework or you're answering questions, I would do it this way. I would do all of the work and then try to answer the questions afterwards. So that way you have everything you need before you have to fill in increase, decrease. You don't have to do the answers in the order they're asked in the homework or on the test. Do all your work, have all of your stuff out there. That way you can then plug in. Here's where it's increasing, here's where it's decreasing, here are the partition numbers. You have everything and you're just filling in the blanks as you go. Let's make that a little different. Let's put in E. So here I have find the increasing, decreasing intervals of 2x minus 5 times e to the 2x. Okay, did you hear that word times? I keep saying, if you hear the word times, you know you're doing the product rule. So let's start that. F prime of x is equal to, I say let's 2x minus 5, take the derivative as 2, keep the e to the 2x, plus, go back to 2x minus 5, keep e to the 2x times the derivative, which is 2. So the first time I took the derivative of 2x minus 5, the second time the derivative of e to the 2x. What do I see? I see a 2, I see a 2, I see e to the 2x, and I see it again. So to set it equal to 0, I think, well, let's factor some stuff out. I'm going to factor out 2e to the 2x, which leaves me with 1 plus 2x minus 5. This says 2e to the 2x times, I'm going to leave the 2x alone, 1 minus 5 gives me negative 4, this is 0. 2 is never 0, e is never 0, 2x minus 4 is 0, when 2x is 4, which means x is 2. Okay. The original function, 2x minus 5, reals satisfy it, e to the 2x, reals satisfy it. So I have this long number line with only one split at 2. Negative infinity to 2, and 2 to infinity. I'm going to be testing the sign of 2e to the 2x times 2x minus 4. I'm going to pick a point. Let's say we pick 1 and 3. So closest numbers on each side. If I plug in 1, 2 is positive, e to the 2x is positive. I'm going to write positive. 2 minus 4, negative. It's decreasing in the first interval. Then I plug in 3. Well, 2e to the 2x is still positive. 2 times 3 is 6. 6 minus 4 is positive, so this is increasing. So this function decreased from negative infinity to 2, and then it increased from 2 to infinity. Where did it change? It changed to 2. It went down, up. This is a min. Okay. We want to find the actual value of what happens at 2, so we're going to plug 2 into 2x minus 5e to the 2x. I'm still going to write this in as f of x equals 2x minus 5, and then e to the 2x. Now I can do f of 2. And it says it's negative 54.598. I'm going to call it negative 54.6. Let's take a look at the graph since we're here. See how it's kind of not there, so I can zoom in a little so you can see it better. You see kind of this point down here. We could change the settings for the x if we wanted to go from negative 20 to 10. And then it looks a little more curvy and not as jagged as it was before. So I'm going to write that in negative 54.6, and we said that was a local min. So one more. Let's find the increasing, decreasing intervals of the natural log of 3x squared plus 1. Right. First thing I want to say is the domain of natural logs is usually positive numbers only, but this one, a little bit happened. The number is squared. Squared makes something greater than or equal to 0. Then I added 1. Now I know it's greater than or equal to 1. So having a positive number, I multiply by 3, I add 1. I know all real numbers can be put into this particular function. Let's start by taking the derivative. Well, the rule for derivatives is you make a fraction. The 3x squared plus 1 goes on the bottom, and the derivative of that, which is 6x, goes in the numerator. We've said over and over, the only way a fraction can be 0 is if the numerator is 0. 6x is 0 when x is 0. 3x squared plus 1, we already said, is greater than or equal to 0, so we don't have anything extra there. So this one partition number of 0 will split this into two intervals, negative infinity to 0, and then 0 to infinity. From here, I'm going to pick a test point, so let's do negative 1 and 1, and then I'm going to put that into the derivative, which was 6x over 3x squared plus 1. Now the derivative in the denominator is always positive, so I'm just going to write positive in the bottom and not mess with it. Negative 1 times 6 is negative, which says decreasing. 1 times 6 is positive, that says increasing. So I had a decrease and an increase, a down and then an up. Okay, down, up. Hopefully by now you're thinking, oh, I know that's a local min. Okay. What do I need to do to get the actual point? I need to find out what would be f of 0. This one is an easy one, so let's go ahead and do it. I have the natural log of 3 times 0 squared plus 1. Well, 0 squared is 0, 0 times 3 is 0, 0 plus 1 is 1, natural log of 1 is 0, so I end up with 0. So this says 0, 0 is my local min. There is more to this particular section that I'm talking about, or the ideas, but I decided to make two videos. So this was the first one to get us through the first derivative test, and then the next one we'll look at some applications and what happens with the graphs of derivatives.